Then it will be later on YouTube. So you can just a moment. Sorry. Yeah, stop transmission. So we are recording. Okay. Hello, Frank. Oh, something with your hand? What's on your hand, Frank? Ah, you are muted. You muted. Okay. So we start seminar. Our speaker today, Professor Yilmaz from Izmir Technical University, right?
Institute of Technology.
Institute of Technology. Yeah. So almost MIT, but another version. So we are familiar with was for many years. He got his PhD from University of Glasgow, right, in 1992, right? So Mark Cooker, as I remember, you got PhD in the same year, right? 92, no? Earlier?
Mine was 1990.
1990, so 2 years before. Yeah, right. And first we met, me and Oz, in 1995. It was again in Glasgow, but at that time Oz visited Glasgow as the visiting researcher, as I understand, for about 1 year, and I was supported by the Royal Society for 1 year to work in Glasgow University, and we work in that Kelvin laboratory, Kelvin Hydrodynamic Laboratory in Acre Road, outside Glasgow. So from that time we working together. We cooperate with Oz. Our research was supported. I believe several times it was supported, but not now. Now it's works on his own topics. And but I still hope that the life will return to normal, and we continue our cooperation as well. So today the presentation will be about three-dimensional dump break flows and small time behavior. So it's about small time asymptotics. Just to say that I'll ask everybody to mute microphones and cameras, please. And I shall do the same. So I will be not visible, but you couldn't hear me, but I will be nearby, and not nearby, just attending. And if something happens, I will interfere. So then, yeah, let's start. So Oz is yours. If you make a short introduction about yourself, correcting my introduction, it's fine. So then everything is yours.
Okay, thank you, Alexander, for the nice introduction and for the invitation. It's a pleasure for me to present this talk here. My last presentation, it was 3.5 years ago in UEA. It was at the campus at that time. And I would like to take this opportunity to wish a happy retirement to Mark Cooker. I read many papers of his, and we had some nice discussions when I was visiting the department. Okay, so three-dimensional dam break flows. I'm going to discuss 3 problems. All of them are suggested by Alexander Koropkin, and they form a part of the thesis of my PhD student, Elona Fetahu. Okay, so I started with this problem to the short time asymptotics. It was at 2009. This is the classical dam break problem. Together with Alexander. And in this paper, we discovered that there is a singularity at these corner points at the leading order, and it was proportional to the logarithm r, this singularity. After that, we were involved in another three-dimensional dam break problem. It was a TÜBİTAK project, Turkish Scientific Research Council project, and Alessandro Efrati was also involved in this project. Again, two-dimensional problem, dam break problem. And this time we have singularities at two corner points, this one and this one here. Okay, and the singularity at this corner point is different from the previous one. It's a power singularity, and this alpha is related to the ratio of the densities of two fluids. So there are two fluids on either side, and there is a wall here. And when the wall disappears, we will have jet formations at the lower parts, at the lower corner points, and a jet formation here, but the singularities are quite different. Okay, so two dam break problems. We are also studying another dam break problem with Alexander with fluids with equal depth. Okay, now this is the first problem. This is actually published in Applied Ocean Research. So the problem is this one. We have a cylindrical cavity here. It's a three-dimensional problem. And at t equals 0, we assume there is a cylinder. So at t equals 0, the cylinder disappears and the cavity collapses. So we want to investigate the short time behavior of this problem. So gravity acting. Now there is an interesting limiting case of this problem. As the radius of the cavity approaches infinity, and as the center approaches infinity, this becomes two-dimensional problem. So once we solve this problem, we should be able to compare our results with the two-dimensional problem. Okay, and we will do that. So that's one problem. And another problem is this one. Again, we have a cylinder, but this time cylinder is not extending all the way to the bed. Okay, it is cut somewhere here. Again, t equals 0, this cylinder disappears. Again, we have a cavity collapse problem. And also for this one, the limiting case is important. As the radius of the cylinder approaches infinity, and as the center approaches infinity, this becomes two-dimensional problem with two fluids. The one we studied in 2013. Let's go back to that one. Okay, it would be similar to, it would be this one in the limiting case. Only difference is that in our case, there is only one fluid in the three-dimensional case. So if you have questions, please stop me and ask questions. Okay, and the third problem is this one. So the fluid is where x is positive and z is between -h and 0. A part of the wall, which is this one, we call it gate, it disappears. And then the flow starts under gravity. Again, when b approaches infinity, it becomes two-dimensional, and we should be able to recover the two-dimensional results. So all limiting cases are useful checks on the validity of the solutions. Okay, all three problems were suggested by Alexander Koropkin. Very nice problems, and I thank him for that. And they form a part of the PhD thesis of Elanov et al. In the thesis, these were the earlier versions. So the versions I am going to describe now, they are slightly improved. Okay, let's start with problem number 1. So the liquid is inviscid and incompressible. So the flow is potential, 3-dimensional and axisymmetric. Okay. So the cylinder disappears, circular cylinder disappears. So there is a cavity here, and cavity collapses under gravity. Okay. The flow is governed by the Laplace equation, and dynamic condition is that pressure is atmospheric at the free surfaces. We have two free surfaces. One is the vertical one at the lateral surface of the cavity, and at the vertical free surface, we have this kinematic condition. And at the horizontal surface, we have another kinematic condition and dynamic condition here in both free surfaces. And the slip condition at the bottom surface. Radiation condition, number 6. Okay. Initial conditions, that means initially the fluid is at rest. And initially the pressure is hydrostatic. And we have unsteady Bernoulli theorem at number 8. Okay. Okay, so we non-dimensionalize the problem. So we use the liquid depth h, and we use a suitable time variable with capital T. Now, epsilon is a small parameter. When it is small, that means we are dealing with small times. And alpha is the dimensionless radius, which is A over H. Okay, so this is the boundary value problem in the non-dimensional variables. Again, we have Laplace equation, dynamic condition, kinematic free surface conditions, slip condition at the rigid bed, and radiation condition, initial conditions, and this is the unsteady Bernoulli theorem at number 16. So after we non-dimensionalize the problem, we assume small time expansions to phi, eta, and zeta unknowns. Okay. We assume that they are valid. Okay, so we will solve the leading order problem. So we replace these expansions in the boundary value problem, which is this one, okay. And then as epsilon approaches 0, we obtain the leading order problem. Okay, one thing we notice in the leading order problem is that this second condition, which is the dynamic condition at the vertical free surface, and this fourth condition, which is the slip condition at the rigid bed, they do not match. If we take the derivative of this one with respect to z, so the vertical velocity is minus t as we approach along the lateral surface of the cylinder to the bed, and as we approach along the horizontal bed, this velocity is 0. So there is a mismatch of boundary conditions at this intersecting circle, okay? So we expect some singularity and some problems there. Okay, so this is the leading order problem. Now the solution is quite easy. By separation of variables, we obtain this solution number 17. K0 is the modified Bessel function of the second kind of order 0. Okay, now two limiting cases we will study here. One of them I already mentioned. The limiting case is the radius and the center of the cavity approach infinity. That means alpha and r, they are approaching infinity, but r minus a is fixed, which is x in this case. We obtain this expansion. So in this limit, actually, to obtain number 18, we are using large time asymptotics of this term, modified Bessel function, and this one in the denominator. Okay, and then we divide these, we obtain this expansion. Okay, so as alpha approaches infinity, we obtain this remaining term. In fact, this remaining term is exactly the same as the solution we obtained in the two-dimensional dam break problem. Okay, so this is we verify that the three-dimensional result we obtain, in fact, is correct. Okay, now there is another limiting case. This time we look at the behavior of the fluid, radial fluid velocity along the lateral surface of the cavity. So if we go back to the problem. So we are looking at the radial velocity along this lateral surface of the cavity. Okay, we calculate the velocity here, and then we split this infinite summation into two parts. And for the infinite parts, we use the asymptotic forms of these Bessel functions. And then after some algebra, we arrive at these results. Okay, now the first term denotes a logarithmic singularity as z approaches -1. That means as we approach the intersecting circle at the rigid bed, which is this one here. Okay. Sorry. Okay. And there are some other terms, but as alpha, which is the non-dimensional radius, approaches infinity, we obtain this logarithmic term. Now this is exactly the same as the one we obtained in the two-dimensional problem again, okay? And this Z0 gives the shape of the vertical free surface. Okay, so next we will plot these results, okay? Now, this figure, we have the shape of the vertical free surface. Now the solid line is the two-dimensional results, and then we have three-dimensional result, and we have equation 28. Now equation 28 is this one. This is the leading order term, and this is the smaller term here. Okay, so we want to see the effect of this smaller term here. Okay, now when alpha is small, that means the radius of the cavity is small compared with the depth, then three-dimensional effects are great. You can see that there is a large difference, but as alpha becomes larger, three-dimensional results are approaching the two-dimensional results. Alpha is 1 here, and 1.5 here, and 2 here. Okay. Also, equation 28 and three-dimensional results are getting closer as alpha becomes larger. Okay, this is again the shape of the initially vertical free surface for small times. Epsilon is 0.01 and t is 1. It was the same parameters for this problem also. Okay. Now, here we vary a over h, which is alpha. So as alpha gets larger, we are expecting that three-dimensional result gets closer to the two-dimensional result. And this is what happens here. At the outside, in this one, alpha is 0.5, and here alpha is 1, 1.5. You can see that we are getting closer to the two-dimensional results. Okay. Now we did the same thing for the initially horizontal free surface. Again, we are getting closer to the two-dimensional result as the radius of the cavity becomes larger. Okay, before the conclusions, maybe I can talk about the inner solution here near this. Okay, let's go back to the figure. Now, since the problem is axisymmetric, we can consider individual points here on the circle. And since the singularity is exactly the same as the two-dimensional problem, the inner solution around this intersecting circle would be the same as the two-dimensional problem. Okay, let's go back to the results, conclusions. So three-dimensional effects become important as the radius of cavity becomes smaller. This is what we observed from the figures. And at the intersecting line, fluid flow has logarithmic singularity when we consider the leading order problem. And the third, in the limiting case, as the radius of cavity and the center of the cavity approaches infinity, two-dimensional results are recovered. Okay. And close to the contact line, the local flow is governed only by the hydrostatic pressure, and we observe this because of the logarithmic term. That's because of this term. This is the first problem. So if there are any questions, maybe I answer them now, and then I move on to the other problems.
Also, I have a question.
Yes.
You are saying that singularity is the same as in two-dimensional case, but it's only for if the cavity is very large, radius is very large.
Yes, correct.
On the other hand, the solution seems that the same singularity, logarithmic singularity, is valid for any alpha. Okay, not very small, not tiny, but for any alpha. And it's like it seems that the displacement of vertical free surface behaves like t squared, some function of alpha coefficient, and multiply by log z, vertical coordinate, I mean distance from the bottom. So, and then it would be interesting to know that function of alpha, right? So that is the another asymptotics. It's asymptotic in terms of distance to the contact line, but there are no asymptotics in terms of radius of the cylinder. Okay, and then you can claim that because the singularity is the same, just parameter or coefficient depends on alpha, then you can claim for that not only for very large cavity, but for any cavity, the inner solution is the same as you derived for two-dimensional problem, but just multiply by the coefficient, right? So then it would be more general result. It's even not question. I believe it's comment.
Yes. Thank you.
It would be good to do that. Okay, thank you. Any other questions? No. Okay, then who is the just a moment. Oh, Mark, please ask your question.
Sasha, yes, thank you. Oguz, the jet in your axisymmetric flow, it looks thicker than for the 2D flow. Is that a correct conclusion?
Actually, let's go back to the figure. So the jet would be axisymmetric from this towards the center, but I mean the jet would be the same if we look at because this logarithmic term and the coefficient is exactly the same as in the two-dimensional problem. So
thank you. Thanks for clearing that up. I wasn't sure, but thank you.
Okay, thank you.
Okay, then we go to the second problem, right?
I think I spent 26 minutes. Is that correct?
Yes.
Okay, so now the second problem actually is similar to the first problem, and the third problem is more interesting. So maybe I skip the second problem and move on to the third one.
Okay.
It would be, I think it is more interesting.
Yeah, good idea.
Third problem, sorry. I was over-ambitious when I prepared the talk. Okay, so this is another problem suggested by Alexander. The wall is along the y-axis, okay? And the fluid is where x is positive and z is between -h and 0. Now this section, this rectangular section of the wall disappears. So under gravity, flow starts, okay? Again, we can check the limiting case when we obtain the solution. As b approaches infinity, it becomes two-dimensional. So we should be able to recover the two-dimensional results. And again, we assume that the liquid is inviscid and incompressible. So we have potential three-dimensional flow, and the flow is symmetric with respect to xz plane. Okay. Here I just present the non-dimensional forms. I am using the height of the liquid to non-dimensionalize. Epsilon again is g times t squared over h, and t is a time scale here. So Laplace equation in the fluid domain, pressure is atmospheric on the free surfaces. So we have two free surfaces. One is the horizontal one, z is 0, and x is positive, this one. And another finite surface is this one. It is where the wall was, okay? So two free surfaces and pressure atmospheric on the free surfaces, dynamic condition. So on the horizontal and vertical free surfaces, we have kinematic conditions. And at the bed, we have slip condition and radiation condition, and initial conditions implying that the fluid is at rest and the pressure is hydrostatic initially. Okay. Again, we assume that this expansion is valid for small times. So epsilon is a small parameter denoting small times. Okay, now when epsilon approaches 0, first we replace those expansions in problem number 1, and then we let epsilon approach 0, so that we obtain the leading order problem. So this is the leading order problem, Laplace equation in the fluid domain. Now the dynamic condition and the kinematic condition at z equals 0, which is the horizontal free surface. Now this one, the third one, they are the conditions on the vertical finite free surface. So y is between minus b over h and b over h, and z is between minus 1 and 0. Okay. And on the wall, outside the gate, the horizontal velocity would be 0. And at the rigid bottom, we have the slip condition. And this one is the radiation condition. And the fluid is at rest initial conditions. Now, again, we have a mismatch of the boundary conditions. Now, at the bottom line of the gate at z equals minus 1, now this condition does not match with this one. Okay, similar to the mismatch we encountered in the first problem. And also, we have another discontinuity. Now, on the wall side, the velocity phi 0x is 0, but on this side, on the gate, we have a finite velocity. So along this line, velocity field is discontinuous. There is a jump discontinuity in the fluid velocity. So it may cause some problems. Other mismatch of boundary conditions along this line, it is the same as the first problem. Okay, again, pressure is hydrostatic. Okay, sorry. Okay, so we look for a solution of this type. We separate the z dependence. Now, this function will satisfy the conditions at the horizontal free surface and the slip condition. So we replace this 44, this suggested form of a solution in the leading order problem 43. Okay. And then we arrive at this two-dimensional problem. Okay. So this is the modified, this is the modified equation. This one, this is okay. Now, at this point, okay, these are the boundary conditions for this problem. Again, we have radiation condition. So outside minus b over h and b over h, x derivative is 0 for this function. Okay, now let's check the reduction to the two-dimensional problem first. Now, as b over h approaches infinity, now that means we have this solution all along the y-axis, and then the solution could be obtained as this one, as b over h approaches infinity. So if we replace this in this series form here, then we obtain this limiting case. Okay, this one at the bottom of the page. Okay, so this one is exactly the same as the two-dimensional problem we obtained. So we have reason to believe that our three-dimensional results would be correct. Okay, and we also want to analyze the local flow near the top corner points of the gates. Now, there are two top corner points. One of them is this one. So here we translate the coordinate system here. And then here we use spherical coordinates. Psi is the azimuthal angle Okay, and so this is the problem near this top corner point of this gate. Okay, so we want to analyze the local flow near this point. Okay, so that is the problem. This is on the wall sides. Okay, this is on the vertical sides. Sorry, on the other side, on the gate sides, and this is on the horizontal free surface and Laplace equation. Okay, so the solution is obtained in this form. So this P is an associated Legendre function of the first kind, and this F is the hypergeometric function. And from this, now we want to obtain the velocity in x direction, which is the velocity perpendicular to the gate. So let's go back to the figure. Okay, we want to obtain velocity perpendicular to this surface. Okay, perpendicular to the gate. Okay, now we notice that the singularity in the velocity is r to the minus 1 over 2. This one we expected actually from the literature. Okay, that was a paper by Koropkin and I forgot the other author. Okay, so we expect something similar. I mean, we obtained something similar here, power singularity, and actually this singularity here we obtained as r to the minus 1 over 2 it will be valid along this line, because along this line we have the discontinuity in the fluid flow in the velocity. Okay, so we obtain this local flow near the top corner points of the gate, which is actually valid along this line. Okay, now we want to solve this. Of course, we haven't solved the problem yet. Now let's look at problem 45. Okay, we still have to solve this, which is this problem. Okay, now we want to solve this numerically. Okay, there is no analytical solution as far as we investigated. Okay, so let's go back to, okay, we want to solve this by an integral equation method. So first we will find the Green's function method for the two-dimensional problem. Okay, so we obtain this using method of images. Okay, problem is this one. We are solving this one. So we are placing another image here for the Green's function. K0 is the modified Bessel function of the first kind of order 0. Okay. Okay, so we assume we draw a large semicircle on the right half plane and use the boundary conditions and obtain this integral equation, which is an Fredholm equation, integral equation of the first kind, and this is the unknown here. This term. Okay, so we will try to obtain this, and the Green's function takes this form in this interval. Okay, and then we use the discrete form of this. Okay, to solve this. This is the discrete form and the Green's function. Okay, we solve this, and then using this integral equation methods. So this is, first we want to investigate the effects of three-dimensionality here. Now the solid line, okay, this is the shape of the vertical free surface. Okay, the finite region, initially vertical free surface. Okay, the solid line is the two-dimensional result. Now, as B over H gets larger, we should be getting closer to the two-dimensional result, and this is what happens here. Okay. And this is the three-dimensional free surface. So the flow is from this direction. Okay, just a three-dimensional view. And this is the horizontal velocity. Okay, we can look at the horizontal velocities along the horizontal lines of the gate. Along the horizontal lines of the gate. So this is y. Okay, B over H is 0.5 here, and T equals 1. And as Z equals 0, that means we are at the top of our free surface. In fact, phi 0 is 0 at that line, and this is the solid line. As, okay, for other Z, other horizontal lines, you can see that we have power singularity approaching here, which we derived it to be r to the minus 1 over 2, okay? So these are the horizontal velocities along the horizontal lines on the gate. So as we approach the sides of the gate, singularity becomes, we observe the singularity, but in the next figure, okay, in this one, we compare this numerical result by this c times r to the minus 1 over 2, because close to this y, I mean, we suspected that the singularity must be of this type, and from this figure we verify this. At the leading order, we have this singularity. Okay, some conclusions for this one. For the third problem, as the breadth to the depth ratio becomes larger, two-dimensional dam break flow results are recovered. Near the vertical edges of the gates, the fluid flow is singular at the order of r to the minus 1 over 2, and the flow along the vertical central line of the gates is very similar to the classical two-dimensional dam break problem. And again, the flow at the bottom should be logarithmic singularity. I didn't talk much about it, but it will be a logarithmic singularity. And I should also mention that we submitted this study together with Elona Fetahu and Olha Ivanishin-Yaman. In the numerical part, Olha Ivanishin-Yaman, she mainly did the numerical parts. Okay. Okay, so this was the final. Thank you for your attention.
Thank you very much for presentation. Yeah, it's yeah, indeed. Second part would take much longer.
Yes.
Yes. Yeah. So but first and third they are quite different, and different techniques used, and different results are obtained. And it would be also interesting to find what's happening at the taper point. So at the bottom, where the face surface, horizontal bottom, and vertical wall meet. Then at that point, as I understand your results, if we go along the edge of the vertical plate to the bottom, the horizontal velocity is square root singular. But if we go along the bottom towards the same point, then the velocity is logarithmic, log singular. So then it's very interesting at that table point to find the interaction of two limiting asymptotics. So this point could be even more complicated than the point on the upper phase surface, where there is a two phase surface, a vertical, horizontal, and the vertical plate, vertical boundary. Yeah, so there is something I believe to do. It's theoretical analysis, but very interesting about interaction of different singularities. And,
yes, that would be interesting. Thank you.
Yeah. Any other questions, please? We still have time. Any other question? Just you can unmute your microphone and ask question. Yeah, Mark, are you asking or you drop your hand?
Yeah, yes, I wanted to ask, I think, about a related matter, which is there is obviously a singularity at the bottom of the wall where the gate is opened, and you've shown that the velocity component in the x direction is singular at the point where you expect it. Can you also expect to have a singularity in the y velocity component along the base of the wall? So if there is a singular behavior there as well, that may influence the direction in which the jet comes out of the bottom of the fluid. It could be coming out at an interesting angle.
Yes. This is a good question, actually. We didn't have a look at the velocity in y direction, and the reason is that from the numerical solution, we could only obtain the velocity in the x direction. So there was no way comparing that result. So, but maybe, yeah, it's a good idea. I mean, we could do that, but we didn't.
Thank you. Interesting work to come out of what you've done already.
Well, could you show equation 48? Yeah. So that is the integral equation.
Yes.
And is that equation of so you said that the derivative under the integral is to be determined, right?
Yes.
How about left-hand side? Is it given? Phi 0 n.
Yes, between minus b over h and b over h, it is given.
Okay.
We can check the figure.
Yeah. So then this equation, is it's called the first order equation.
Fredholm integral equation of the first kinds.
Yeah, first kind. Okay. So such equations are difficult to solve, and but also in that equation G is with log singularity, with logarithmic singularity, which helps to make a matrix after discretization diagonal dominated. So to solve it. However, my question is that function under the integral d phi dx, that is the normal velocity in x direction on the vertical phase surface. As you said, this velocity is square root integral at the ends of the
rectangular section.
Yeah. So did you use that in numerical procedure that your solution is square root singular? Did you kind of impose from the very beginning?
No, we didn't. We didn't, no. But Olha did the numerical part. Maybe if she's attending the talk, maybe she can comment on this. I don't know. Olha Ivanishin.
Yeah, I saw her.
Okay.
I saw her.
But I mean, we didn't impose. I already know we didn't.
So you assumed, solving that equation, you assume that normal derivative is to be determined is the finite.
Yes, yes.
And it's like a piecewise constant approximation you used for discretization? Or
Yes, for the discretization, we used the one used by Iafrati in the paper 2013.
Okay.
Yes.
Okay. I understand. Right. Any other questions? Any other questions? Okay,
And also, I forgot to mention, we received also help from Alessandro Iafrati in solving this equation.
Okay.
We asked him some questions and he replied, so.
Okay, thank you. Then we are closing our seminar. Before closing, before stopping recording, I see that we have many external participants today, and my messages to these participants, external participants, if you think to present your results and discuss your results at our seminar, please send me email with the say title and short abstract of your potential presentation. All our seminars this semester are on Mondays from 2 to 3 London time. At all weeks are already assigned, so we are completely booked this semester. However, quite soon we will start inviting speakers for next semester. So if you like to be visible in University of East Anglia, please send me email and suggest the topic for your presentation. It's for everybody. I'm not saying this to my colleagues from the School of Mathematics, because I always saying this to them, inviting them to show their results to our other colleagues. Then, then any other comments about anything? No? Okay. Then I stop recording.